Okay, let's continue with the ZEUS training, Section 8, Aerodynamic Modeling Guidelines. So the first modeling guideline here is to always check the mesh before running the Euler solver. Oftentimes you can visually see problems in the mesh that need to be corrected before running the Euler solver, which will then just blow up and you'll have to investigate why the solver's failing to converge. So the first option here is to use the plot arrow bulk data card to output the mesh. And then you can specify solution -1 in the executive control command, which stops execution of ZEUS after the mesh is generated. And then you can use TechPlot to view the mesh. So some key points here of how to generate a good overset mesh. For the smaller block embedded in a bigger block, the grid densities at the boundary of the smaller block should be comparable with those of the bigger block to minimize the interpolation errors. And the ratio between the grid cell sizes of the two blocks doesn't have to be exactly 1:1, but 1:10 is too large and not acceptable. And the reason for that is, as I've mentioned before, with the overset strategy, the embedded block will actually not solve the flow solution in the outer two cells boundary. The outer two cells are used to strictly interpolate the flow solution from the parent block. And then that flow solution in those outer two cells is held constant and serves as the boundary condition for the inner cells of the block during the solution. So in this example, we can see these outer two cells here will receive an interpolated flow solution from the main block. So it takes the flow solution from these cells in the main block, interpolates it to the outer two cells in the inner block, and that's done around the entire boundary. And then during the flow solution, of course, the inner blocks are solved where the outer two cells are held constant. So for that reason, you want the mesh density to be somewhat comparable between your embedded block and the main block. Likewise, the inner cells of the inner block, so excluding those outer two layers of cells, will hole cut into the main block. So wherever we have these inner cells on the inner block, those cells will be used as donor cells and contribute the flow solution back to the main block. So those cells in the main block that are in the interior portion of this embedded block will not be solved during in the Euler solver. They'll simply be held constant where the solution is interpolated from the child block, the inner block. So some additional ways to help with that grid density matching is on the XY plane. You can tweak X growth or X lead and X trail, which are defined in the mesh param and the block cards of the smaller block, to improve the mesh. And then the X lead and the X trail of the smaller block does not have to be extended too far away from the store. So in this example, our store boundaries are here and here, and you can see that the X lead is out this far ahead. So it's approximately the length of the store here. We have extends in front of the nose is the length of the store, and then the aft, the length of the store extended back behind the aft point is where X trail is. Whereas for the overall model, this block, if this block was the only block in the solver and we were only solving for the store, the X lead and X trail would have to be much farther away. But for the embedded block, you don't want it too big. Because the reason here is you want to have the embedded block be big enough so that it can capture the flow characteristics of the flow flowing around the store, but then you want to contribute that flow solution back to the main block, and you want the main block to be able to solve the flow characteristics of the overall aircraft. Okay, moving on the YZ plane, we can use dy fact, y growth, y left, and y right to tweak the span-wise z lines, and use dz fact, z growth, z bottom, and z top to tweak the horizontal y lines. And for a surface mesh that's intersected by other embedded volume meshes, 2 layers of donor cells on the upper and lower surfaces of this surface mesh are always retained. So in that case, let's see. So in this block, we actually can't see the store pylon, but we have a store pylon in here, and the pylon extends all the way to the boundary. Now earlier I said that the outer 2 layers of cells of this embedded block are always receiver cells. However, where the pylon comes up to the boundary of the block, those volume cells that are directly adjacent to the pylon do remain donor cells, or they're cells that will be computed by the Euler solver for this embedded block. So this is because the boundary condition is applied on the surface mesh, so that the volume cells near the surface mesh must be donor cells. And then we want to minimize the overlapping region between the surface mesh and the embedded volume mesh is a good overset mesh strategy. So in this figure, the black lines are the global volume mesh on the wing. The red lines represent the wing surface mesh, which is here. And then the blue lines are the embedded store volume mesh domain here. So minimizing the height of the embedded store volume mesh so that it barely touches the wing lower surface mesh is the goal here. So if this embedded mesh just touches the wing, that's what you want. You don't want the embedded mesh to extend up on top of the wing, because if the embedded mesh is on top of the wing, then when you're interpolating the flow solution, you're actually getting flow that's flowing over the top of the wing that contributes to the boundary condition of the embedded mesh, which is obviously incorrect. So you want this embedded mesh to be completely below the wing, so that the interpolated flow solution in those boundary condition cells is correct. Next, vertical lifting surfaces with a sweep angle. Now, if you try to why can you not do this? So if a vertical lifting surface has a non-zero sweep angle, it cannot be fitted into the XZ plane of the block of mesh, because all of the chordwise Z lines projected on the XZ plane are parallel to the Z axis in the block of mesh. Thus, they cannot accommodate the sweep angle of the vertical lifting surface. So what must you do? The vertical lifting surface with a sweep angle must be fitted into a separate block of mesh. And in this block of mesh, the vertical lifting surface is treated as a horizontal surface lying on the XY plane of a local coordinate system, so that the mesh on the local XY plane can be sheared to accommodate the sweep angle of the lifting surface. And this can be achieved by defining the block of mesh to be located in a local coordinate system with the A-chord bulk data card specifying entry of theta equals 90 degrees. So now this vertical tail locally in this embedded block of mesh is a horizontal surface. Now, if you do try to put this vertical lifting surface into the main block, into the XZ plane, ZEUS will then model the vertical lifting surface as a straight wing with 0 sweep angle. This is obviously incorrect and will probably lead to large errors in the computational result. ZEUS will print out a warning message, but you shouldn't attempt to do that. Just put the vertical lifting surface in its own block of mesh. Now, of course, the one example here is the block T, the T-tail block of mesh, which can accommodate both the horizontal and the vertical lifting surfaces. Next, we'll look at the Wingbody Junction. So the width of the rectangular box to model the body is determined by the Y-zone definition, and it is usually equal to the maximum width of the body surface mesh. So if the root of the tail is not at the location of the maximum width of the body, or wherever this Y-zone boundary is, then part of the tail is embedded in the rectangular box to model the body. And this part of the tail cannot be accounted for in the boundary condition of the flow solver, so no flow solution is computed on this part of the tail. So in this example, we have the wing up here. So this is where the Y-zone is. And we have our body it's curving back here so that the horizontal tail comes back to here. So these panels, you can see, are inside the body box, because the body box boundary is where the Y-zone is. So these panels are inside the body box and no flow solution will be computed. However, at the end of each time step, ZEUS will extrapolate the solution from the computational mesh onto the surface panels. Therefore, this part of the tail embedded in the body mesh box will still have a flow solution by the extrapolation from the solution on those nearby tail panels. And this extrapolation will only extend for 2 panels. So if you have a lot of panels here in the spanwise direction, it's more than 2, the extrapolation won't work beyond 2. So if you do have this situation and it's just a small region and it's only 1 or 2 panels wide, that is acceptable. Just be aware that ZEUS will take the volume flow solution that's out here and extrapolate it onto those panels in order to get the surface CP on the tail. Next, we want to use the gap or the gap 1 cards to improve the mesh quality on the XY plane. Now for a fuselage wing tail tip launcher configuration, the mesh region ahead of the wing leading edge resulting from the line tracing method could be poorly distributed. So without these gap cards, you can see that we have these Y lines here on the body, which will be extended out in this direction by the line tracing method, and then we have these Y lines from the tip launcher, which will be extended out this way. Now there's no guarantee that these lines will match up. In fact, they'll probably miss one another, and so you'll get extra Y lines, and you'll have an uneven distribution of Y lines within this region. So 2 sets of chordwise Y lines could be generated, one from the tip launcher and the other from the axial stations of the fuselage. Now the chordwise Y lines between the trailing edge of the wing and the leading edge of the tail are originated from the axial stations of the fuselage in here. And this could result in a poor mesh spacing for those chordwise Y lines. So we use the gap or the gap 1 bulk data cards can control the mesh spacing in these regions. So on the left we have without the gap card, so you can see that we have the uneven spacing of these grid lines, and that's because we have the lines coming from the fuselage, the lines coming from the launcher, and that's just what we end up with. Meanwhile, ahead of the tail, you can see that we have a very large spacing here of lines ahead of the tail. So the flow solver will have trouble with this because it has a really large volume box size followed by a really small volume box size, and we want to avoid that. We generally want the sizes of the boxes to be smoothly varying. So we can fix both of these problems with the gap cards. So the gap in front of the wing here, we can manually line up the lines from the launcher and the body so that we have a nice smooth looking mesh. And then back here, we've redistributed the spacing of these lines so that we get a smooth growth. We have a small boxes here from the tail, and then they grow larger to get large, and then once again they grow smaller to get back to the size of the aft size of the wing. So this is a much better mesh. And then next we want to look at using the gap Z to improve the mesh quality on the YZ plane. Now similar to the gap or the gap 1 bulk data cards, the gap Z cards provide a means to control the spacing of the horizontal Y lines on the YZ plane. And for a fuselage wing tail configuration, if the wing and tail are not on the same plane, then we have 3 horizontal Y lines between the wing and the tail are created by the automated mesh generation scheme. And the second set of horizontal Y lines between the wing and the tail are generated from the body surface mesh. And these 2 sets of horizontal Y lines could result in a poor grid spacing on the YZ plane as shown in this figure. So above and below the tail, we have some lines being generated, and then above and below the wing, we have lines being generated. Meanwhile, we have lines from the fuselage being generated, and you can see once we combine all of these sources, we get a poor spacing of lines. So by adding the gap Z card, the spacing of the horizontal Y lines is under user control, and then furthermore specifying nseg equals -1 in the body 7 card deactivates the generation of the horizontal Y lines from the body surface mesh. So now if we look at our new model, our gap Z is defined here, and we have a smooth distribution of horizontal Y lines in the Z direction. Next, we want to look at modeling a wing with a large dihedral angle. So the automated mesh generation scheme can generate a sheared mesh on the YZ plane to accommodate the dihedral angle of a wing-like component, as shown here in this figure. Now, because the span-wise Z lines on the YZ plane are always parallel to the Z-axis, the orthogonality of the mesh resulting from the lifting surface with the large dihedral angle may not be acceptable. So these boxes in here are very highly skewed. So for a highly skewed mesh, the Euler solver may fail to converge. So this is a poor mesh because we have highly skewed boxes here in this region. So to circumvent this problem, it's recommended that the winglet be modeled by a second block. Now note here that Y left of the winglet block, which is right here, is set at the root of the winglet in order to avoid the intersection of the winglet block with the surface mesh of the main wing. So we want the main block to be able to compute as much of the flow associated with the wing as possible, and then we want the winglet block to be able to compute the flow for the winglet and then contribute that solution back to the main block. So that's accomplished by setting Y left of this block to be at the root of the winglet. Furthermore, we've controlled the theta angle of this block so that this line here is not canted too severely. Notice if we made this block normal to the main section of the winglet right here, then this angle here would be very steep, and so we would have many more boxes from the winglet block overlapping with the main block. So we would have fewer boxes here in the main block that could be solved by the main block. They would be overlapped and hole cut by the winglet block. So to minimize that, we've made the winglet block normal to this section of the winglet. And then these boxes in this region are still skewed, but they're not skewed as severely as these boxes were. So this is an acceptable skew angle. This is not an acceptable skew angle. So this is a good overset scheme. Now, as we said before, when using overset, that may decrease the solution accuracy a little bit because now you're interpolating among blocks. However, this is a much better scenario than this with these highly skewed boxes. Next, we want to look at the Y zone for the indented wing-body junction. So an indented wing-body junction means that the body width is wider than the distance between the roots of the right-hand side and left-hand side wings, as shown in this figure. So the figure on the left, but these two figures show an incorrect Y zone definition, where we choose our Y zone to be at the boundaries of the fuselage, and then we have our wing penetrating into the body box. So all of these wing panels will be inside the body box, so we won't have a flow solution here. So the Y zone containing the body is defined according to the width of the body, and any components like this wing here inside the rectangular box for the body mesh established by this width are excluded from the computational mesh, which will lead to incorrect results. So the correct thing to do here is the correct Y zone definition for the body is used as the distance between the roots of the right-hand side and left-hand side wings. So now the whole wing is outside the rectangular box for the body mesh, and thus it's within the computational mesh. And the slopes of the true body surface are mapped onto the rectangular box for the body boundary condition, and the resultant pressures are mapped back to the true body surface. Therefore, the final aerodynamic forces are calculated using the true area of the true body surface. Therefore, no aerodynamic forces are lost. So this resulting dashed line is our body box. So you can see that the Y zone definition is determined by the wing, not by the body. And this works just fine. So now ZEUS will take the slopes from this entire body because it knows that this body is in this Y zone here, and it will map all of the slopes of this body onto the body box. And then the flow solution can be solved using the transpiration boundary condition. Next, we want to avoid large sweep angles of a C arrow 7 adjacent to a body 7. So here in the figure in the right, we have a high sweep angle strake leading edge, as shown here. And then these black dots here are the centroids of the volume boxes that are adjacent to the fuselage body box. So you can see that the centroid for this box would be about right here, and then we have the centroids of these two adjacent boxes here and here. So modeling a strake with a high sweep leading angle by a single ZEUS macro element, as shown here, can generate highly skewed computational volume mesh adjacent to the fuselage box model. Now, the boundary condition for solving the Euler equation on the fuselage box model is applied at the centroid of the volume cells adjacent to the fuselage, shown by the solid black circles. So that's here. And the ideal volume cells adjacent to the fuselage box are orthogonal to the box surface mesh. And this orthogonality obviously is violated such to the extent that the flow solver fails to converge. And we know that this is the problem because we removed the wing from this model and ran ZEUS with only the fuselage, and it ran just fine and converged. Next, we left the wing intact and removed the fuselage so that there was no fuselage, and ran ZEUS, and it ran just fine. So we know that the problem is that we have these highly skewed boxes next to the fuselage, and so when ZEUS maps the boundary condition onto these volume boxes, that's what is causing the problem. So to circumvent this problem, we're going to break this ZEUS macro element into two ZEUS macro elements as shown here, and then adjust the sweep angle of the strake here. So now we have kind of a fake wing with just a little bit of extra area. You can see that the true strake here is just a straight line from this point back to this point. And here we've extended the leading edge forward, so we have a little bit of additional area, but not too much. So here, the ZEUS macro element adjacent to the fuselage has a smaller leading edge sweep angle, as can be seen. And this reduces the skewness of the volume cells adjacent to the fuselage surface mesh, as shown here. Now, the allowable sweep angle leading to a converged solution varies case by case, because if you just look at this model, you may say, actually, that's still a pretty steep sweep angle. And I would agree with you. Yes, that is a pretty steep sweep angle. However, it's less severe than this angle. And when we ran this model in ZEUS, it converged just fine, and we got an acceptable solution. So the sweep angle faithfully representing the true model leads to a convergence problem, and we use a trial and error process to artificially reduce the sweep angle for the Euler solver. May be required to reduce the sweep angle by a minimum amount. So once again, just by moving this leading edge point of the ZEUS up by a little bit, reduces this sweep angle, and this now creates a model that can be solved by ZEUS. And once again, to diagnose this problem, we have our entire model, and if we remove the fuselage only from the model and then run ZEUS, the Euler solver will converge just fine, and we'll get acceptable results. On the other hand, if we leave the fuselage in and we remove the wing and all these associated components, ZEUS will run just fine. So we know because of that there's an interaction between the fuselage and the strake here that is causing the problem. And that leads us to a few troubleshooting ideas of how to troubleshoot failure of convergence of the CFD solution. So first, set the print convergence equal to 2 in the MK param card to print out the convergence history. Now for a steady flow solution with only a 2-order residual reduction, the solution is marginally converged. A well-converged solution requires at least 4 orders of residual reduction. So the first step is make sure that the steady flow converges nicely. If you have poor steady flow convergence, then you're more likely to have the unsteady flow not be able to converge. Next, the surface mesh containing a large slope with respect to the x-axis often causes a convergence problem. So a very refined surface mesh near the leading edge of a wing with a round leading edge can create such a large slope problem. So typically in the CFD world, you'll see people want to make very fine meshes, and especially near the leading edge, have a very refined mesh to capture the shape. In ZEUS, it is possible to make your model be too refined. So when you do that, you have a very large slope at the leading edge, and that can cause the solver to fail to converge. So if you suspect that's the problem, make the wing more coarse, especially near the leading edge. Coarsen that wing up, and then see if you can get convergence. Secondly, the mesh on the inlet face has a large inclination angle, or it could, for which the flow-through condition must be specified by the P-body 7 bulk data card. So if you have an engine inlet with boxes that are nearly normal to the flow, if you set them as inlet boxes, then that will help the flow solver be able to converge. If you fail to set them as inlet boxes, then of course the flow will see these boxes with a huge angle, and the Euler solver does not like that. You can use the plot slope bulk data card, which we saw previously, to generate plot files of the slopes on the aerodynamic mesh, and that will allow you to quickly identify visually, based on the color, where those large slope boxes are. Next, it's desirable for the CFL number to be as large as possible, because larger CFL numbers result in a faster solution convergence. However, larger CFL numbers can also cause the solution to diverge, in which case the CFL number should be decreased. And in some cases, more artificial dissipation is needed by increasing the Viz2 and Viz4 parameters above their default value of 1. And it's recommended not to raise Viz2 and Viz4 above 1.25. So if you're failing to converge, the first thing to do would be to try reducing the CFL number. Once your CFL number gets down to about 1.5 or 1, and it's still failing to converge, then I would recommend increasing Viz2 and Viz4. So try 1.05 or maybe 1.1, and that will increase the artificial dissipation, and then see if you can increase your CFL number up to 3 or 4 to get the solution to converge. Now, in our experience, most of the convergence problems are caused by a poor computational mesh, usually between two aerodynamic components. So to find out where the poor quality mesh originates, you can activate the free comp or the free component option in the param bulk data card. Now, by default, all of your C-Aero7 and Body 7 elements that you have in your model must be referenced by a block 1, or block T card. So all of your aerodynamic components must be represented in your volume mesh. If you don't do that, ZEUS will print out a fatal error message. But for debugging purposes, we have a parameter called freeComp. So when you set the free component parameter to 1, then ZEUS will allow you to have surface components not referenced by the block cards. Now in this case, any components that are not referenced essentially are not seen by the ZEUS Euler solver. So it would be similar to just deleting or commenting out those components. So you could, if you wanted to, comment out the C07. However, that can cause other issues because you have lots of bulk data cards referring to that C07, and it can just get very complicated very quickly. So the easiest thing to do is activate the free component option, and then that will allow you just to not refer to that particular C07 or that particular Body 7 from your block 1 or block T cards. So after you do this, run the steady flow solver with a few aerodynamic components at a time, and then repeat the procedure, except leaving out other aerodynamic components in the model until the source of the mesh problem is identified. Now you can't just do a strictly binary search because oftentimes the problem isn't due to just a single component. The problem is due to the interaction of two components. As we saw in the previous slide, the wing alone ran fine, the body alone ran fine, but when you combined the wing and body together, that's what caused the problems. So just be aware of that as you're selectively removing components from the flow solution.